Hi, so this video is about Hess's law, which has to do with enthalpy, determining enthalpies of reaction in chemistry. But I'm actually going to start by showing you this image that's from problem 5.6 that we had as a homework problem. And this was in the problem itself, it was specifically related to internal energy rather than enthalpy. But we can use it as an illustration of enthalpy because, like enthalpy, internal energy is a state function, which means that it's path independent. It only what matters is the initial and final states, not how you got between them. And so one of the questions in problem 5.6 asks you to determine the difference in internal energy between state C and state D. And you'll notice that there isn't actually an arrow here connecting state C to state D. But you can use arithmetic using these delta E1, delta E2, delta E3, delta E4. You can use arithmetic to work out what the difference is between state C and state D, because again, these are path independent functions. And so what's true for internal energy is also true for enthalpy. If we were thinking about a series of different reactions, if each of these delta E's represented the enthalpy of some particular reaction, we could work out the enthalpy that it would take to get from state C to state D without ever doing that reaction, because we could simply use the numbers we had determined from other reactions and just do simple arithmetic to work out what the enthalpy of reaction would be in going from state C to state D. And so we can determine delta E between state C and state D using arithmetic. And again, if we transfer this over, which we're going to start talking about now, to enthalpy, we could determine delta H for a reaction that we never actually run by using delta H values from other reactions that we have run. And so let's take a look at some examples of this. So delta H is well known for a lot of different reactions, but it's not convenient, or even sometimes, like an example I'm about to show you, not really possible to measure delta H for every reaction we're interested in. There are some that would be very, very difficult to measure delta H for them. But we can use published delta H values for reactions that have been run to work out the delta H values for a reaction that hasn't been run and in fact would be very difficult to run. And so let's think about an example of this, and let's talk about carbon monoxide. So carbon monoxide is different than carbon dioxide. I think you've probably heard that carbon monoxide is actually a very poisonous gas. And so which is why you never want to start your car in a closed garage or in any closed space, because carbon monoxide is a product of the incomplete combustion of gasoline, and it's very, very poisonous and toxic. It binds very tightly to hemoglobin and prevents oxygen from getting in your system. You essentially suffocate yourself. So you don't want to be breathing carbon monoxide, but it is a product in very small quantities of pretty much any combustion of a gasoline or other hydrocarbons, because it's rarely the case that combustion is 100% complete and goes entirely to carbon dioxide. Sometimes you often get a certain amount of carbon monoxide. Now, suppose you want to actually determine delta H for this reaction, the combustion of methane, and we've written the combustion of methane several times. But here, instead of writing the combustion of methane to give me carbon dioxide, which is the typical product that we write for combustion of methane, I'm writing this to give me the product as being carbon monoxide, and it changes the stoichiometry a little bit. If I was making carbon dioxide, this would be 2O2, but I'm making carbon monoxide. Well, there's a problem with trying to find delta H for this reaction, and that is that it's essentially impossible to run this reaction. In other words, if I take methane and just put 1 mole of methane and combust it with a mole and a half of oxygen, what I'm likely to get is a lot of carbon dioxide and a lot of unreacted methane. It's just extremely difficult to kind of stop this reaction halfway and have it give you all of an intermediate product that's on the way to the final product. So it's essentially impossible to run this reaction. But we can still work out its delta H, its enthalpy, because we can simply use a couple other reactions that are easy to run to work this out. And so here's a diagram of this. So if you think about it, the combustion of methane in oxygen to give you carbon monoxide is simply a stop on the way to the combustion of methane to give you carbon dioxide. The second step of that would be reaction of carbon monoxide with oxygen to give you carbon dioxide. So if what we're interested in is knowing this delta H2, the enthalpy of combustion of methane to give me carbon monoxide. But that's the thing that's very difficult to measure. But if I can measure this one, the blue arrow, the complete combustion to carbon dioxide, and then I can measure the value for taking carbon monoxide and burning in an oxygen to give me carbon dioxide, I can simply subtract delta H3 from delta H1 to give me delta H2. So here's what Hess's law says. Hess's law says that if a reaction is carried out in a series of steps, delta H for the overall reaction is going to be equal to the sum of the delta H's for the individual steps. And so we can use this in a lot of ways. If we didn't know delta H1, but we did know it, 2 and 3, we could add them together to get 1. If we didn't know 2, we could subtract 3 from 1 if we knew both 3 and 1. If we didn't know 3, but we knew 1 and 2, we could get 3 by subtracting 2 from 1. And so let's see how this works out. Because delta H is a state function, then as we've said before, the energy changes are only a function of initial and final states, and how we get from this state to that state doesn't matter. Delta H is only a function of initial and final states. So what form would a problem like this take? Well, here we go. So it turns out, like I said, taking methane and making sure you've got a huge excess of oxygen so that the methane burns completely to give you carbon dioxide is fairly easy to do, and it's well characterized. Getting a sample of carbon monoxide, which is also, there are many, many industrial processes for generating pure carbon monoxide. You can get it by heating coal with water in the absence of oxygen will generate all kinds of carbon monoxide. And you can purify it, and you can then burn that with a huge excess of oxygen to give you carbon dioxide, and you can measure that enthalpy. And so here's what a problem would look like. You're given the following. For the combustion of methane, the complete combustion of methane to give carbon dioxide and water, delta H is negative 890 kilojoules, which is a number we've seen several times before. And we can take pure carbon monoxide that we've generated using some other method, and we can burn that in oxygen to give us carbon dioxide. And these are both reactions that are very simple to do, and it is simple to determine the enthalpy changes for those reactions. Now, this is asking us to calculate instead what is delta H for this reaction, the partial combustion of methane to give carbon monoxide in water, which, as I said earlier, that is a very difficult thing. Okay, so let's think about what we're given. We're given these two equations and their enthalpy changes. We want to know the enthalpy change for this reaction. The way that you do that in practice is to try to manipulate these two equations so that they will add up to this one. And so the way I would do if I was looking at this would be to say, I'm going to look at this equation at the top and say, well, it's got methane on the left-hand side, which is what I want for my summed reaction. It's got oxygen on the left-hand side, which is more or less what I want for my summed reaction. And it's got water on the right-hand side, which is what I want for my summed reaction. So I'm just going to leave this one alone. If I look at this reaction, I'm thinking, well, I need to cancel out carbon dioxide. And so I need to have the carbon dioxide on the left-hand side here to cancel out the carbon dioxide that's on the right-hand side up here. And I need carbon monoxide to be a product, whereas in this reaction, it is a reactant. So what if I just reverse the reaction? So I'm taking this reaction and I'm making the product, CO2 is now the reactant. and the reactants over here, carbon monoxide and oxygen, are now the products. Well, we learned earlier in the chapter that we can do that manipulation, and when we do that, how does delta H change? Delta H changes by just simply changing the sign. The magnitude of the reaction is the same, but the sign is now different. And so now, having done that, I'm just going to cross out the original reaction that I had written there, because I have this now in the orientation that I want it to be. Now you see that the carbon dioxide on the left cancels out carbon dioxide on the right. And this half a mole of oxygen is going to cancel out some of these 2 moles of oxygen to leave me with 1.5 moles of oxygen. And so now you can see I've got what I want. Methane plus 1.5 moles of oxygen gives me carbon monoxide plus 2 moles of water. And so when I add them up, that's the equation I get. And then I simply add up these two enthalpies, and that gives me, so negative 890 plus positive 283 gives me negative 607. And as you'll see, that's exactly what the number was that was written here. So what we've essentially done is taken delta H1 and subtracted out delta H3, and that gives us the delta H for a reaction that we can't run, but whose enthalpy change we can measure indirectly. Well, another useful thing of Hess's law has to do with what are called standard enthalpies of formation. And so standard enthalpy of formation is defined as the enthalpy change that is associated with the reaction in which 1 mole of a particular compound is made from its constituent elements in their elemental forms. And so that's a lot of sort of funky language, but what does it really mean? It means that the standard enthalpy of formation of liquid water is whatever the enthalpy change is for the reaction in which 1 mole of water is made from its constituent elements in their standard form. Well, the standard form of hydrogen is H2. The standard form of oxygen is O2, both as gases. So to make liquid water from them, it's going to be 1 mole of gaseous hydrogen plus a half mole of gaseous oxygen will give me 1 mole of liquid water. Similarly, if I was going to do carbon dioxide, the reaction to make carbon dioxide from its constituent elements is going to be solid carbon, in this case graphite is the standard form of carbon, plus gaseous O2 gives me 1 mole of CO2. So, here is actually a table of standard enthalpies of formation for several compounds. There's maybe 24 or so compounds listed here. There's a much, much larger table in the back of your book, Appendix C, that we've talked about before, and you've actually seen me going and looking in. And so, but these are standard enthalpies of formation, and under standard conditions, which would be 1 atmosphere of pressure and 25 degrees Celsius. So that's just one thing to point out. When we were talking about gases, the standard temperature was 0 degrees Celsius or 273 kelvins. But for all this thermodynamic data, this standard temperature is 25 degrees Celsius. And so we can just pull, I just decided to pull one out of here. Let's look at calcium carbonate. So it says for calcium carbonate that the standard enthalpy of formation in kilojoules per mole is negative 12.07, negative 1207.1 kilojoules. That means, so if the table says that the standard enthalpy of formation of solid calcium carbonate is negative 1207.1 kilojoules, that means that delta H for this reaction, that is taking 1 mole of calcium plus 1 mole of carbon plus 1.5 moles of oxygen to make 1 mole of calcium carbonate, has a value of delta H of negative 1,207 kilojoules. Now, this is an interesting reaction, actually, and I didn't initially pick this thinking this, but it occurred to me later that this is another example. I'm sorry, let me just back up for a second. The other thing is that by definition, elements in their standard states have a standard enthalpy of formation equal to 0. So because all these reactions are enthalpy changes of compounds from their elements in their standard states, then the elements that they're in their standard states are by definition have enthalpies of formation of 0. But I was thinking about this reaction that I picked it, and then I got thinking about it some more. This is another great example of a reaction that would be really, really difficult to do. So that number negative 1207 was undoubtedly arrived at not by actually doing the reaction shown here, but by using Hess's law, because it would be very difficult to get calcium and carbon and oxygen, 3 different things, to react together in one reaction to give you solely one product. Because there are all kinds of other products that could come out of this, like calcium carbide and carbon monoxide and all kinds of crazy things. So this is another example of using Hess's law to arrive at a number. Here are some reactions that you can do that are easy to do and easy to measure the enthalpy changes of. One would be to burn calcium and oxygen to give you calcium oxide. Another one would be to burn carbon and oxygen to give you carbon dioxide. And then to take carbon dioxide and calcium oxide and react them together in a reaction that gives you calcium carbonate as a product. And then if you notice, I'm not doing a full treatment of this, but you notice now that there's calcium oxide on the right and on the left. There's carbon dioxide on the right and on the left. When you add these things up and cancel those things out, you just get calcium plus carbon plus 1.5 moles of oxygen gives you calcium carbonate. Okay, what is the value of these standard enthalpies of formation? Well, the value of standard enthalpies of formation is that it allows us to calculate the enthalpy change for any reaction for which we have standard enthalpies of formation for all of the components of the reaction. So here we're talking, for example, about the combustion of propane. And so this reaction doesn't actually occur this way, but again, because we're talking about state functions, we can treat reactions as occurring any way we want them to occur because the path doesn't matter, only the final and initial and final states matter. So you can imagine this reaction actually occurring in 3 steps. The first step being propane decomposing to carbon and hydrogen, and then carbon reacting with oxygen to give carbon dioxide, and then the hydrogen reacting with oxygen to give water. And if you add all these things up, the carbon cancels out the carbon, hydrogen cancels out the hydrogen, you get propane plus water plus oxygen gives you carbon dioxide plus water. Once more, the reaction doesn't actually occur this way, but because of Hess's law and the state function nature of all these things, we can treat it mathematically as though it occurs this way. And it adds up to the balanced equation. Okay, so we can use Hess's law in this way, and this is an equation that you really want to get your brain around because it's going to be used a lot, not only in this chapter, but in other chapters involving enthalpies of reaction. We'll also see this same equation for entropies and for what are called standard free energies of formation, Gibbs free energies. But what this means is the enthalpy change for the whole reaction is equal to the sum of the enthalpy changes of the products. I'm sorry, equal to the sum of the standard enthalpies of formations of the products minus the sum of the standard enthalpies of formations of the reactants, where N and M here are the coefficients from the balanced equation. And so for the reaction we were just talking about, the combustion of propane, we can simply say, all right, if you look in Appendix C, you'll find that the standard enthalpy of formation of carbon dioxide is negative 393.5 kilojoules. For water, it's negative 285.8 kilojoules. For propane, it's negative 103.85 kilojoules. And for oxygen, because that's an element in its standard state, that is 0. So it's products multiplied by their coefficients, 3 here for the carbon dioxide, 4 for the water, minus reactants multiplied by their coefficients, 1 for the propane, 5 times 0 is 0. And then you're just doing arithmetic to get to an answer here, which for this reaction would be negative 2220 kilojoules. Let's try one more example. This is the combustion of methane that we have talked about in class before. It's kind of one of the most common reactions that we write in AP chemistry. And so if you look in Appendix C, it will give you these values for the standard enthalpies of formation of all these substances. Negative 74.8 for methane, 0 for oxygen because it's an element in its standard state. We just saw these numbers earlier, negative 393.5 and negative 285.8 for carbon dioxide and water, respectively. I set this up. It's 1 times carbon dioxide plus 2 times water, the sum of all that minus the sum of the reactants, 1 times methane plus 2 times oxygen. Simplify those by multiplying the coefficients through. Simplify even further by adding this side together and then adding that side together. And when I add the whole thing together, I get negative 890 kilojoules, which is what we've seen before as being the enthalpy change for this reaction. So that's Hess's law. That is standard enthalpies of formation, and that is how to use standard enthalpies of formation. And so I will post, along with this, some suggested practice problems to prepare you for the QOD. And thank you for watching.